right, last part of this very long problem. We're now adding 0.05 molar of NaOH. Now we're adding some strong base. So let's first look at the dissociation reaction of strong base, NaOH. So we have NaOH. It fully dissociates in water to form sodium ion and OH minus. And we have 0.05 molar NaOH that we're adding. So for the ice table, we start out with 0.05, 0, and 0. Then the change is that it's fully dissociating in water. So this all gets consumed and forms ions, which then gives us at equilibrium no NaOH, 0.05 molar sodium ions, and 0.05 molar hydroxide ions. Okay, so next thing to think about is what happens with the base reaction when it reacts with conjugate acid. So what's happening is we have acid, NO2. It's reacting with base to then form NO2. Really, you know what? I said base reaction with conjugate acid. Oh, this is our conjugate acid, right? Conjugate acid is HNO2. We're adding hydroxide to then give us our base, which is NO2 plus water. So this is the reaction that we're looking at. Now, what happens is we started out with, this is the same as our weak acid, 0.1 molar HNO2. From hydroxide, we get, from the dissociation of hydroxide, we get 0.05 molar initially. And then we start out with 0.1 molar of NO2 minus. Where does that come from? Again, the dissociation of the electrolyte or the salt, because we have salt that's also present with the weak acid, 0.1, and then we know that we don't do anything with water. Now what's the change? So again, like we did in problem 2, when we had the acid and we had the protons that were formed, all of those got consumed and reacted with the conjugate base. This time, all of the hydroxides from the sodium hydroxide is going to be consumed and reacts with the conjugate acid. So the change then is once again going to be 0.05, where all the base is going to get consumed and reacted. So that at equilibrium, we end up with 0.05 molar conjugate acid. We have 0 OH, and then we have 0.05 of our base. All right, so now we're in good position to solve for the pH. But as you see, this is with base. So I recommend that we use this equation. We solve for the pOH by using the that long name, Hasselbalch equation, pKb plus the log of conjugate acid, which is HNO2, over base. We have everything that we need almost. We just don't have the Kb. But no fear, we can solve for it, right? We remember that we have the Ka, and Ka times Kb is equal to Kw, which means that Kb is equal to Kw divided by Ka. And we know that the Ka is this. We've already calculated Kb before. It's 2.22 times 10 to the minus, I think 10, right? So that's our Kb. Yeah, that is. Okay. So now we have everything that we need to solve for the POH. So that means POH is equal to the negative log, right? Yep. Of 2.22 times 10 to the minus 10 coming from here, plus the log of our conjugate acid concentration, that's this, 0.05 over the concentration, something's weird. Okay, that's because I didn't add that. This is supposed to be 0.015, so 0.1 plus 0.005 equals 0.15. Concentration of our base is 0.15. And so now all we have are numbers, and we can solve for the POH. The POH ends up being 9.176. So we can then figure out that the pH is equal to 14 minus 9.176, which gives us a value of 4.82. So, recap, if we add some sodium hydroxide, some strong base, we get a slight increase in the pH. It goes from 3.35 to 4.82. Let me make an important announcement, I guess, point. Part 1 was independent by itself. Part 2, we added hydrochloric acid to the buffer. And then for part 3, we added sodium hydroxide to the buffer, as in starting with how it was in step 1. We didn't add NaOH after adding some HCl. That'd be something different. We're looking at just if we add sodium hydroxide to the buffer, and then if we add hydrochloric acid to the buffer, okay? So as we see, we get a slight increase, like we should. It's not too much, but we're going to compare this ratio a little bit later. All right.